大家好，我是王木老双半糖。从现在开始呢，我们开始用英文授课了。All right. Today I'm going to talk about TSMC and Intel, CoWoS, EMIB, Foveros and Chiplets. This is part of my class about introduction to packaging process technologies. And as you know, that TSMC is not currently number one in semiconductor manufacturing, and their strengths, not just in high yield or 3 nanometer or even 2 nanometer. Their packaging is also not just one of the best, but actually the best among the three giants, TSMC, Samsung, and Intel. And their process, of course, is more than CoWoS. They have their 3D fabrics and everything else. But today I'm going to focus pretty much on CoWoS only, and then we'll explore the other arena when ready. And Intel has this EMIB and Foveros. And I'm going to talk a little bit about chiplets, which is hottest topic right now that everybody want to say, can we do chiplets? And I want to explain why, what are their pros and cons of chiplets. Now, before going forward, we also, of course, have to understand what are the KPIs for packaging technology. People call it P3C2. It's mentioned by Douglas of TSMC. He says that people are looking for performance, power, and packaging profile. And of course, that's 3P. And then the C is cycle time and cost. Cycle time is how fast you could make it to the market. And of course, the bottom line is how much it's going to cost the customers, whether they're willing to pay for the cost of fabricating all these fancy packages. Here I see something that they don't have. They don't mention yield and reliability, which I think is the engineering perspective the most important one. Because the customer don't care. This is what they want to have. But from the process technology perspective, yield and reliability are the key decisive factors. And with this in mind, the heterogeneous system integrations that eventually we're moving forward with continuous pitch scaling. You want to go to 36 micron to a couple of microns, right? That's the smaller the better because you can pack more stuff there. And that's always true. And is more than more you pack, more different stuff only on one same into one same package. That is very challenging. But today we will focus on TSMC and Intel, and let's look at what they actually have done to their packaging process technology. This is TSMC this year's in one of the key conference that they published their 3D fabric. They call it 3D fabric. Okay, and they have silicon stacking and advanced packaging. They stacked up silicon with salt C, salt P, salt X. These will talk separately. For the advanced packaging, we're going to focus on CoWoS. Info we'll talk in the future as well. CoWoS is interesting to me because it focuses on silicon interposer. And this is a very good idea. And we're going to go a little bit deeper about what silicon interposer for and means. And they keep advancing. This thing keep advancing because of the customers' needs. And their updates, they said they are focused on high performance computing only because that's where the big customers are, right? NVIDIA, AMD, Intel. They're all working on this specialty servers, right? They're all high computing, high performance computing markets, right? That recently NVIDIA's CEO says that the market for current currently the AI server that need to be that can replace in U.S. alone is $1 trillion to the year of 2030. You can see that that where the big market and the money are, right? So they want to basically integrate this the high bandwidth memory and logic. This is pretty much what they try to do. We look at some of the products they have and go over details. But if you look at this, the true customer, they only have 25 customers. They're all big guys. So the advanced packaging is not for small guys because they don't have that money, because that really is costly. You need to put a lot of chips there, right? So you need to have a lot of chips ready and then so put it on one package. So only, few customers can afford that. And they said that there are more than, or roughly 25 customers. Among them, only a few big ones. Apple, right? And these NVIDIA and AMD, Qualcomm, and pretty much that's it. It's a top five, actually. The rest is not as big, right? And the product is not that many. It's 140. It's not like if you look at the silicon product, that's thousands, right? But here, the player only a few handful. Either you buy an Apple cell phone, all right, or Qualcomm's Pixel, or even Google cell phone. They all have this logic with the memory. So there are not too many products. All right, so their CoWoS product is about 140. Now each one take about say 5, something like that. But one of the key things they mentioned is that they're developing the 6x reticle size RDL interposers. RDL interposers means that there's something inside silicon. They are not just the center silicon. There's something is buried inside redistribution layer. There's something the signal can go inside the silicon. So the silicon interposer is not only something to support everything, but also as a communication route. Why bigger is better? Why 6x reticle size? What the reticle size means? Why is 5,000 millimeters square? Right? And then this is what they say they're going to do. They want to have 12 HBM, 12 memory stacked together and with the logic inside, CPU and GPU inside, right? And this is what they say they're going to do. And this is outstanding, 6x. Previously had only 3x. See, this is in 2021, they have 3x. 3x of reticle size. It's about 2,500, right? And here you're gonna 4x currently you have, but they're gonna move to 6x, right? So this is currently they're gonna do 4x. And here I would like to explain what reticle size means, right? So people can, when you read a paper or read something related to the packaging size, why they always use these reticles in the packaging area in the unit of reticles, right? What that means. And you can see that CoWoS is the largest one at this moment. This is 2017 publication, and they are now 3x right now, 2021, and now they're moving to 4x already. And in future, they move to 6x. And you can see that the impact of this, all right, why TSMC strategy is much better than Intel from this perspective. And here I'm going to explain what reticle size means. The reticle size means that a reticle has a field. That's the area, that's the maximum size of a die which currently a lithography tool can do. Meaning that this is what they can print, right? This is what they can print. 26 millimeter by 33 millimeter. And this is the size of an image. You could call it an image from the mask to the wafer. So if you are a wafer and you look at the light shining on top of you, and that field is only 26 times 33 millimeter. and that is 858 millimeter. And this is a universal value because that's what the SML tool, almost all the little tool is doing. It give you a feel of that size, even though the lens could be huge. It does not matter. The size of the mask is 4x. So the light, you can imagine light shining through the mask. Mask is 4 times larger than 26 by 33. That's it. So the mask collect the light with a pattern, and then they shine this pattern on top of the wafer with a size with a 4x reduction of 26 by 33. And this is universal. And then so you cannot have, pretty much it's difficult, extremely difficult to have die sizes of a product bigger than this, because how do you print half a die? Right? You could say, I want to put 2 dies in here. That's okay, right? This doesn't matter. Mass gun's just going to print 558 millimeter every shot, right? So you could put as many die inside as you like, but have to be conformed to this rectangular shape. It's not square though. It's also rectangular. Okay, that's the crazy thing about the litho. Let's not go over details. In this picture is explaining to you that actually for the high NA mask, this does not work anymore because it turns out that they print this way. The mask is printing this way. The mask is 26 by 33 at 4x in XX, but AX in y-axis. This means that they have problem printing a die with only this area. So suppose you want to create a die larger, right? You have to print twice, and that's what's happening right now for the high NA. Then the Intel had a problem with that, so they say, why can't we make a larger mask? This current mask is 6 inches, so you can see this 6 inches mask. All right, so it's fine. So this is the area going to print eventually, but with a 6 inches mask, you could do that by amplifying 26 by 33 4x on the 6-inch die. Perfectly fine. But with the new demand for high NA, because they need to print it twice, they need to have a 9-inch mask. All right. And 9-inch mask, nobody want to commit to it. That's the problem. It's too much work. Okay. And so that's it's still in struggle. If you're interested, you can come into this lithography update, checking into it. But anyway, that's the reason if you say 6x, 26 by 33 times x is 5,148. And that's exactly what TSMC meant. He's developing a 6x reticle size. Reticle size is a universal unit. So they would do this to cover all technology. So that's pretty much the reason why they choose reticle size. And it's easier. Otherwise, you would say 2x. This is 16,000. You put 16,000 here. Nobody understand what you're talking about, right? Putting the reticle size is kind of is a visual aid, pretty much. Okay. Now, let's look at one specific examples. All right. That this is a size method. Here we have the size method. Another size method is the die size. NVIDIA H100 is one big GPU with 6 memory chips, right? And this is what they have. This one, and the GPU is the GH100. They have 80 billion transistors, all right? And the die size is 814. You can imagine that they cannot go overboard, right? They cannot design a die which is bigger than 558. There's no way. So they are limited in the die size they could generate. They use N4 M4 process to do that. So this is a spec. That's not what we're talking about. What we're talking about here is that such a big die. What about the yield? What happened to yields for such a big die? They just give you a baseline TSMC for the NVIDIA 10 that the die is very, very small and less about 1 centimeter by one is 1 centimeter square. So it's 100 millimeter square. So it's 8 times less. The yield is 80%. Okay. So this, and also Apple's 80% for their die size is about 1 centimeter by 1 centimeter, which is 100 millimeters square, and their yield is 80%. And this is what I calculated for them using this data and using Poisson statistics to generate a formula for you. The yield reduction as a function of area. Right? This is a formula I generate for you, and you can see it's always decreasing in decreasing manner, meaning that the larger the die, the lower the yield. It's just Poisson statistics. It's nothing fancy about that. And then let's take a look at what we can my explanation in a short video I have. In this video, I explained that the particle landing on a wafer is just like a bomb landing in London in the World War II. It's practically a Poisson distribution, right? Then they will put resources to protect those areas more, right? So, but they don't know how to deal with this problem. So what happened is that one of the scientists, our Clark, he did this. He divided the area by the number of grids, the whole London area to 576. And then he, of course, he know how many total bombs that's been dropped. And then he also know the drop in every area, which area it be dropped inside this grid. So this is the probability come up. All right. This is the probability he figure out and using, and then plot it here. So the blue one is the red one is the actuals, and then the blue one is the one predicted by the Poisson ratio, by the Poisson equations, by the Poisson distributions. Then you can see that it matches very well. So what's that mean? That means that actually it is a random event. The Poisson distribution assumes a random. So when German airplane come out to bomb the London, they don't have a specific target in their mind. They just drop it when they are reaching the area, just drop it random. So this means that to British military, you don't have to do anything specific. You have to warn the whole city, but you don't have to focus on specific areas because they are random. And then so therefore you could focus on the resources in a better place. Okay, so that's a very famous Poisson distribution examples. And if you use that if you treat that to silicon world, we will do the same thing. What I meant is that contaminants and particles are landed on piece of wafer. It's just like German bombs on London. They are actually similar from the eyes of statistics. Okay, we previously mentioned that the TSMC 5 nanometer is here, 80%. And then if we assume that these are generated by certain defects, certain particles in this case, right? We assume it's random. And the particle, there are many different type of particles. Just some inner particles, done. So these zero here, you put K0 equal to 0 here, and then you put into the formula here. As I explained, a particle landing on wafer is also Poisson. based on the Poisson distribution and then the further refinement of these distributions, people come up with a negative binomial distribution. This is what the IRTS recommended, all right? And then I use that to calculate, all right? So I use this data at Apple III A13 die size with this value, okay, close to 1, just make it up. And then this is what I come up with, all right? So you could use different scenario by assuming what kind of value. This example, specific example is assuming 0.44 to 0.44 centimeter in size. And then I use this simple calculation to generate this formula, right? It does not, and that's how I got this value. And this is for 1 by 1 that, sorry, it's not Apple 13 anymore, it's something else, but it does not matter. You could use this formula instead, all right? So, but the story is that it always decreasing. So it was you're high, you're sort of high in this small die. The die size around this area around this area that TSMC is doing a very good job in making the yield 80 and 80, 90% in this area. But when you go down to 4, you drop, to 50% already. So imagine you drop to 8. So this is like 30% or less. Yeah, put it at 30 to 40%, assuming, some fudge number can go on into the calculation. So you will still see a significant reductions for the die, to be a die yield to be smaller, and it will stay low. It doesn't mean that if I got a big die, I got a 30%, 40% yield. If I keep working on it, it will become larger. Yeah, it will become larger, maybe at 1 or 2%. But there's no way to come back to these 80%, 90% value, right? So they will stay low. And that means a big impact to the factory capacity planning. You have to plan to generate more wafers for the same amount of die coming out from the factory, right? So this is the key that I would like you to remember. The larger the die, the lower the yield. And in fact, TSMC recently announced that they will give NVIDIA a super hot run status, meaning that their wafer will run faster, like 2x faster or something like that, so as that they will come out with the same amount of good die at the end of the delivery date. So you can imagine that's the impact. They have to run faster. And then with more wafers inside, they generate the same amount of dies coming out. So the die size, that's matters, all right? And let's keep looking at CoWoS, Chronicle CoWoS of TSMC. And I always feel interested, if you understand some company strategy, it's good advice that you go and visit. This is what we saw previously. And so this is when you go to this website, TSMC website, you can see a plethora of many products they come out. And then I'm interested in NVIDIA's Tesla GV, this Tesla GV 110, 100. It obviously is for Tesla product, right? And then that Tesla product, they have the high performance computing HPC, as I mentioned, all right? And then they have the 32 gig memory. So that's what the HBM goes. So pretty much that's what they do, right? This NVIDIA chip is obviously AI chip, all right? That's NVIDIA's V100 Tensor Core, right? And then that's the beauty of it, okay? And then it'd be interesting to look at the NVIDIA's performance and looking at how exactly the chip works, right? And everybody's going to high performance computing. So that's the key. So, and everybody, that's where the markets are. So it's not like a silicon chip. You have 28 nanometer, you have everything else, but those But those and then even 40. But in the packaging world, it seems that the high performance are that's where the monies are, at least, right? So when you have time, please go into and check into this foundry TSMC about their process, right? But what in fundamentally a CoWoS is just an integration of chips on a piece of silicon. This silicon, the green part, is they call interposer, which is a bridge, a conduit that allow electrical signal to pass around, and these lines are embedded inside the interposer. These days, interposers are getting more and more complex. The routing are more complex and more capable. So and they had to place as close as they can, right? So as that they will not lose the speed. Ideally, you will stack all together. You will stack them all together, right? That's your ideal world. So ideal world, you could stack everything on top of each other. Memory, you could do that, but to put memory on top of CPU is a big deal because you could think about the stress and then the thermal property of each component are quite different. I/O has a much higher voltage. CPU memory. This one, if it depends on what kind of memory you put it there. If it's DRAM, right? And then they will leak a lot, right? And CPU will run very fast. Temperature could be very high, right? So I need a fresh memory here. So all these had to work together, and each component had different electrical requirements. So their temperature are different. This one going to be hottest for sure. This one maybe, right? And so with a different temperature, put it together. If you put it in one, everything in one, that actually is hard. What the silicon is doing, silicon has pretty reasonable thermal conductivities, right? Pretty good among all the materials, and it's very rigid. The Young's modulus is very very high, 130, 150 gauge, right? So Pascal, and so and it's, by the way, very cheap. And you want to make lines in here, you better to be silicon, right? If you use other material, how do you make lines? It's a lot of work, cost. So its flow is like this. So it's silicon. So this explains the flow of us interposers. This is what at the end of the day they would do. All right, die one and die two. So they will go through this purple one is interposer. And then you can see that the packaging, the substrate, as the PCB board you have that are all connected. So interposer is something in between the die and the packaging, and your PCB pretty much. And now you are putting everything together, connected by this high-speed link, because they're all connected. All this distribution, you call it RDL, redistribution lines. These are all RDL lines that they pre-manufacture inside the interposer. And then you have to make sure they're all connected properly, right? Without connecting properly, there's no signal. Imagine if one broke, then these two die cannot communicate with each other, then it's pretty much dead. Remember, the problem of packaging, the process technology, that the requirement of yield, the cumulative yield, is very stringent, because you have one good die and there are two good dies here, and you want to connect on interposer. If you fail to do so, these two die dead. There's no chance of rework. So you can imagine you already spend money on this, spending money on that, and then you connect it. If you connect it wrong with the low yield, you lost two dies. The cost is 2x or even higher, because the cost of silicon interposer is expensive as well. How do you dig holes, right? How do you dig holes? That's TSV. It's called through through the TSV is the via they go through, and that is very expensive. Okay, and there's micro bomb and all that. TSV is a through via that connect interposer front and back, right? So this is a hardcore one. That's the cost is highest in the through silicon via. You have to through it, and then this why it's so expensive? Because here is copper, right? And you're gonna dig copper in a big way. These are all micron, tens of, maybe hundreds, at least tens of microns deep, and size are large, right? And so TSV, and then it's for copper, and then you have to electroplate, and this process is slow, and overall it's costly. It's not like we use copper line, the back end of the line, which is reasonably fast because the line is very small, right? It's a nanometer, 10, 20 nanometer. And here you have micron size, couple of micron size. So to dig that deep, it's difficult already. It would take etcher a long time to dig a hole and then a long time to fill it up. So so the cost is not the machine, it's the time that consumed. So that's why they mention the cycle time, right? In our in this P3C2 indicator, the cycle time is very important. If it takes forever to do so, and then you don't know whether you're going to come out good or bad, it's pretty nasty to deal with. Okay. And so this is a big picture. And CoWoS is a 2.5D interposer. And then that's what they say is it's a chip on wafer on substrate, right? And here is their their technology, of course, included. See, these HBM they get stacked together, right? Through TSV everywhere. These are all TSVs too. The die had to go through, right? And then here is a micro bomb. Here the bomb, very small, much smaller than the regular bomb. So everything had to work. As I said, the logic and graphics side by side, and then there's a base die to manipulate this the HBM DRAM to talking to this device, right? And inside, you also need to have some kind of capacitors. So we're not going to go detail here. This is just the process that going into the silicon interposer. That's where TSMC shines. It make this process work. Is Samsung, Intel knows about that? Of course they know. You just like do a simple reverse engineering, cut it up, and that's what people do, right? The wiki chip do that, and or even the company will review by itself, and then company is a stack. They know every material been put into to make the whole thing work. But why they cannot make the whole just copycat it? Because there's a lot of IP and a lot of hidden process technology that TSMC holds that, of course, nobody else knows. And this process secret make them high yield, and that's the key advantage. Okay. Now this is we didn't spend a lot of time going through the details of how each layer worked. That will be in a future talk. This talk is geared to make sure that the overall process, the comparison that I intend to do makes sense to you. So that's all. Right? So the detail part, I'm going to leave out a little bit, except the big picture. If you look at the Intel process, they call it EMIB. They are kind of interposer, but in a different manner. They are not silicon. They are silicon inside organic substrate. So there's interposer, you can imagine, it's not silicon, it's an organic interposer. But inside is organic, they are silicon inside. This part is called micro, it's kind of micro bridge. It's a 2D scaling. Silicon bridge embedded in an organic substrate. And then and then they talk at the edge. Okay. And then they also talk across it, but the important signal you're probably talking to here. And so this is the detailed picture that they show. And then let's look at this advertisement, right? It'll be interesting to see. Let's look I always like to look at people's, the company's advertisement video. It can review some interesting stories. Let's look at it. Look at that, they say the size of 2.5D solution is limited. And let's check with let's recall what TSMC did, right? They are moving to solve that problem to make it so big. Okay, so this limitation is no longer can be is to be removed quickly. If you look at it, they put this silicone thing inside and then started create trenches on top of it in an organic material. That just make me feel uncomfortable because, as you know, in the future, if I want to scale these things, you can imagine, what I will do to my scaling. It's going to be hard to make holes and then fill up with copper inside plastic in a very small dimension compared to silicon, right? So this one, I immediately see that's a problem with the EMIB. And of course, they could say, I'm very flexible. I connect Taiwan and Taitu with everything. It's in true, it is flexible, but silicon interposer can do the same thing, right? So I don't see the advantage of this yet. So that's what he says, right? The configuration, that's the industry standard, pretty much TSMC. They said that the configuration doesn't work as the die is not large enough to connect all these pieces. But that's not true. Right now they have a very big one, right? They have 3x already, and then 4x already, and 2023, and then more moving to 6x. So this thing, what Intel says not working, is no longer stands. So anyway, so this is a picture. People, you could go and take a look at it and see what you think, right? And if you look at the EMIB pros and cons, right? So from the previous video, and we could this summary did a pretty good job. It's pros, okay, and then the larger die count. It's a piece of plastic, right? That you are trying to embed your silicon bridges into, and theoretically you could put as many as you like, right? You do have the flexibility. Do have the flexibility. As far as the lower costs, I don't know. That I don't know. Because that you have rely on specific tools to handle the trenches, right? These are copper wire inside the polymer. I don't think it's an easy job, right? And the problem you mentioned, I could not agree more. It's a thermal the coefficient of thermal expansion are different. Things I mentioned that the die one and die two could be in different temperature, and so is the plastic is not a good thermal conductor, so it will keep heating up. So you do something to keep the things cooled down, and then when the polymer heats up, its property changes. So the many things could change that is not be a good boy. Not like silicon. Silicon, you run it 100, 200, no problem, right? Pretty much no problem. Uh, and you cannot say the same thing for polymers. So you can imagine that its customer currently only a few. The first customer is a Graviton 3 from Amazon. The rumor says that the die were fabricated in TSMC for 5 because that's the only one there. The TSMC is the one that have 5. Nobody else has it, right? Or has it with a big yield. But then they package in Intel with EMIB, right? So this is what people find out with the reverse engineering. So of course, the Intel worked with this customer specifically and doing a reasonably good job. There's no doubt about it. And but and but the question is that if you do a summary about the pros and cons of CoWoS against EMIB, right, with the same I/O, and you can see that EMIB has claimed to be many good things, and then CoWoS it has this stress problem. That's for sure too. Right? But it itself has the stress problem, not much stress problem, but thermal problem, as I previously mentioned. Right? And then the cons, the interposer size limited. This no longer stands. Okay. The capacitance issue, that's true. That's true. But you could make it thinner, you can make it some work, it can be done. Okay. And then the insertion loss is higher because the polymer are different. That makes sense too. And overall, they agree that the organic substrate manufacturability is a little bit not good, right? The bottom line, we need to be high yield and fast throughput. And now you're introducing a different interposer to this factory and then try to make everything work. It's a challenging task. And so Intel moved to suggest another one, Foveros. And the AIB only have a few customers. They are working on the new stuff. Then Foveros is die-to-die stacking with direct copper bonding. So it's much fancier. They don't need TSV anymore. No, there's no TSV. So what they do to me is the Foveros has a fancy interposer. All right, that's my way of explaining it. There are two silicons. One top is compute, the other one is the base. Right, so everything related to the computing on top, they put on the base, as you can see here, and then they connect it die to die with this micro bomb. All right, okay, but this bomb in a way that supposed to be direct bonding, direct copper bonding. So direct copper bonding means that inside each wafer, you have the connection already that you pre-manufactured on bottom and on top, and then you bond them together with direct bonding, which is I think invented by the IBM. A very good idea. But the copper is naturally has a heavy oxide here, right? To bond them together, first of all, you need to have polishing very well. So the bottom of the wafer, you have to thin it down and polish it, and then and then very well. But copper, as you know, is easy to have dishing, the dishing problem or erosions. And then you want to bond together, you need to have a many innovation here. Uh, Recently, you can see a lot of paper on this innovation and how to bond them together efficiently. And here is the just one example. When you bond with a material, if there's SiO2 around it, this material has to bond as well. The direct bonding is just not copper; it's everything on the wafer, right? So that is tricky, right? Because the stress from the thermal expansion are very different. Temperature and SiO2 are very different. So the thermal stress induced, it could be tricky. And then when you go to big size, and the size goes up, the process margin obviously goes down because you need to make sure every bonding works. And I'm going to talk about direct copper bonding a lot in the future, the seminars that I'm going to present. All right, what people deal with this problem. It's a very interesting problem. And but right now, I'm sure TSMC working on it, but there's no report on that. They're going to move into that anytime soon, right? Anytime soon. So the last part of my talk is focused on the chiplets, right? So what's the big deal about chiplets? The driving force, the way I see it, for chiplets, the technology is that the better die yield, right? And its flexibility. You just mix and match whatever you want, pretty much, and stack them together. That's that I call it PowerPoint idea. It's always so good, right? And then you have massive parallel mounting the highest accuracy. That's what you want to do, 1 micron size. Previously, this is all, say, even the Foveros, 36 micron bump pitch. And then you want to go directly to your chiplets, say 1 micron. This is almost 2 order magnitude improvement in terms of accuracy. And that is very hard. So when you look at the development of semiconductor industry, they do incremental. They don't do revolution. If you do revolution, you just pretty much get killed very easily. If you look at Samsung, gate all around development in 5 and 4, and they fail, they move to 3, and then move to 2, right? It's difficult to change architecture that easily. And TSMC, on the other hand, won't do that. They stick to FinFET until even 3 nanometer with N3E, N3A, N3X, all kinds of N3, meaning that they can stay there as long as they can before they move to N2, which is gate all around. And Samsung, on the other hand, they want to move to gate all around, it's a fancy gate all around, and 5 and 4, and they got dinged pretty bad, right? We all know that story. But chiplets is another one like that. But the fundamental driving force is better die yield. Why is it better die yield? Because the smaller the die, the higher the yield. As we mentioned, NVIDIA 5 is 80%, and Zen 2 has a smaller 84%. The Zen 2, AMD's Zen 2 chip is smaller, and so it's 84. Right, so this is the beauty of the TSMC process. But if you look at this is what they show up in what they have shown in one of the paper or conference they published. In here, you can see that this die yield is 80%. Die 80%. There's so many dies here. 32, 52 maximum die per wafer. That's 3,000 wafers. So the die is very small. That's why it's so big. And if you say that chiplets, if you make fabrication chiplet, the smaller the die, the higher the yield. As I mentioned before, if you have your 80% here, and then if you reduce your die size to here, you will become the higher yield by nature. And if you say, I want to do a large die, and you are in here, right? So this is all curve from all these famous statistics, all these mathematicians. They come out with different distributions of Poisson, Murphy, C's, Bose-Einstein, negative binomial. All these are predicting how fast the die, how fast the yield drops with the increasing die size. All right, and then but on the other hand, if you decrease in the die size, you got immediate new bump. So that's why the chiplet, people want chiplet, because you can see from the NVIDIA, their die size is a whopping 814 millimeters square, pushing the limit to the field size of a little tool. And that, of course, dropped the yield to about 30-40%. And then the factory had to run much faster to accommodate that loss. And if you make a chiplet, then the factory in manufacturing the die itself could naturally have much higher die. If you remember that the hard drive chip, the chips for the hard drive, is so small that defect doesn't matter. They don't care about particle at all. Nobody care about how clean the tools are, because every defect is being isolated. So there's no point working to make the tool very clean. They're isolated, right? The particles even want to kill one die. But if you have 10,000 die, kill 100 die, who cares, right? But if you have a couple hundred dies and one particle kill one die, then you cannot tolerate that loss, right? So it's just a number game, right? So chiplets, the first advantage, and as pros and cons, the smaller the die, the higher yield is a major advantage. The cons is what? So this is what chiplets is all about, right? It connect everything. This is PowerPoint presentation. It's just like EMIB, right? All verbals. You just say the component A, high yield, 95% yield. So I'm going to put it together and connect it. Yeah, right. Yeah. But the packaging is a nightmare. But the more you packaging, then the more difficult it is, because you are saying that the chiplets, so these three here, every one of them has 100%. The cumulative yield. So you cannot, it's difficult to have a redundancy in this part, right? Each one, you have to have perfect. The connection had to be perfect. So from the process engineering side, it's very difficult to do experiments, to test, because the DOE will be very costly, since you have to have many components to do one experiment, right? So in that sense, that it's not going to be easy task. So when you do TD work, to moving forward to a new technology, you need to do a lot of process development, and this is very costly development. So that's why it's slow. Is the development is so slow, and TSMC is working on it, but this is far from maturity, of course. All right, a couple of years away. We'll see how it goes. But that brings out a story that I think is interesting to tell to close this talk. So why TSMC is so much more successful compared to Samsung and Intel? All right, because they start easy before going overboard. They don't want to go. This is my personal opinion, of course. They start easy before going overboard because they want to have a solid baseline. This is the key. You need to have a very clean baseline to do any technology development work. Otherwise, you don't know what you're getting. If your baseline is very noisy, all right, then you get a signal from your TD wafers. You cannot tell whether it's true or not, because the signal to noise ratio is so bad if you have a lousy baseline, you know. And then this solid baseline, I think, is key strengths of TSMC. Intel also has a good solid baseline. To be frank, to be fair, And then here, I think is where it start differentiate. They attract many customers to get process learning because TSMC always say that I'm not going to compete with my customers. I'm just fabricating whatever they want. I'm not going to make a product out of it. On the other hand, Intel and Samsung, they make their own product. So the customer will be hesitant to go there because if they go there, say, what about if you capture my learning into your own product? Well, I'm going to protect my own IP. That's always in the back of the mind. And so that one make the customer's number goes up for TSMC tremendously. And I think the one that most people don't know is that the TSMC grow local supplier to enable flywheel effect. I explain this later, which means they work closely. Taiwan is such a small island. The supplier will cluster around TSMC and provide the best service they can. And TSMC will come into their fab to help them to grow. Say, I have a need for special gas, I have a need for special chemicals, and then I need you to develop this for me to save me money. Otherwise, I had to go out, and then had to fly my supplier, find my supply here. That's very costly, even with the same cost of productions, right? So they did a pretty good job. And then the supplier are very they are very obedient in a way that they work closely with TSMC to get a business. It's just a win-win solution. So this I call it a form of flywheel effect by Jim Collins, right? And then in turns that is forming a positive feedback loop for yield learning. That's the fundamental reason that TSMC has such a good yield learning, because all the chemicals, all the tools, the parts they use, as many as they can, come from a supplier they qualify by them or individually, and they help them develop a new spec. And then the what I meant by flywheel is that the building and link together that many parts. These are suppliers, right? Our supplier, and this is a big TSMC. The wheels start to turn, and these small wheels turn and help them, and this big wheel also come back. Help the small wheel to turn. So it is a flywheel effect, right? So that's beauty about this. So it's a positive feedback loop for your learning that make TSMC stands out. In turn, Intel doesn't really do that. US is so big, it's difficult to have all the customer come to you in a cluster format, which you do, right? Apply and then a lot of small supplier, big or small supplier, they cluster around the TSMC, Intel. They try to do the same thing, but it seemed that TSMC did a better job. Okay, but the end result is this: the TSMC IP portfolio is mind-boggling big. All this IP portfolio, they are free to use. For the designer to come in and say, hey, use this IP or all kinds of technology you need. I will show you a product that meets your need in a quick and cheap manner. Right? So this is the major strength of TSMC. They have a huge amount of IP portfolio. Intel is an IDM factory. They manufacture their own product. So they don't have a customer learning. Every customer has their own specific demands, specific requirements that you don't know unless you work with them. That's exactly what TSMC did. They work with the multiple suppliers, multiple customers, and they have met all kinds of problems. They solve their problem. They work together, forming a work group. They solve together, come up with something new, either IP or invention or something that come into this bank, this IP bank, that eventually to share with everybody else. So they are attracting more and more customers because of that. So here is another positive feedback loop, right? And that's the key reason why TSMC I see is so successful compared with Samsung and then the Intel, right? Both of them don't have that many IP portfolio. I think both of them combined cannot even beat TSMC in this aspect. simply because the way the business model in the beginning is not right. No wonder Intel break away the new manufacturing into foundry now. So that's interesting to see. All right. So that's my talk about. This conclude my talk about Intel, TSMC, and Intel CoWoS, EMIB, Foveros, and Chiplets. And I hope you get a roughly good idea about what's going on before we delve we dig we, before we do a deep dive into the process technology aspect. You need to have a big picture, right? What problem you try to solve, what customer you have, in order to get you going. All right. Thank you. That's my talk.